How about if we have a gas mixture? We still can use PV equal to nRT. However, we have to do some modification whereby we have to consider the species, each of the species. Okay, so the pressure is no longer P, but the pressure is PA, which is a partial pressure of A, whereby the pressure that would exerted by a mole of A alone in the same total volume at the same temperature. So instead of P, it's become PA, partial pressure of A. Same goes with a mole. N is a total mole. If you have A or B, or A and B, which is a mixture of gas, when you have A and B, so you will need a partial pressure of B and A, and together with the mole of B, A. From this partial pressure, you can determine a mole fraction of A. Okay? When you divide, when a partial pressure divided by total pressure, it will be equal to the YA, which is a mole fraction of a gas. Okay, and we have this equation whereby sum up all the mole fraction is equal to 1. Okay. And then when we have partial pressure of A plus partial pressure of B is equal to how much the mole fraction times a total pressure, YB times P is equal to P, and this is called Dalton law. You will learn in detail about this law in your thermodynamic subject. But here, it's enough for you to understand that when you have a gas mixture, so from P it become a partial pressure of A or B is a summation of A, B, C, regardless how many species you have. The total pressure is a summation of each pressure, whether it is A, B, or C, or D, or regardless how many, and sum of it is a total pressure. And from this partial pressure and total pressure, you can determine a mole fraction of A. And it is called Dalton law, which is a partial pressure of a component of an ideal as a mixture add up to a total pressure. Okay? So meaning to say, if you sum up all the partial pressure, it will be equal to total pressure. Same goes when you have a volumetric flow rate. The same ideal gas, but in terms of volumetric flow rate, instead of changing the partial, the P become partial pressure, we changing the V become a volumetric for that particular species. Okay, and from here also we can determine the mole fraction of A, which is this one. Okay, when you have a volumetric of A as a part of, let's say in this container you have A and B. Okay, so you can choose to use with the partial pressure of A plus partial pressure of B equal to total, or you can choose to use a volumetric of A plus volumetric of B equal to total volume. Okay, and we just change, if you notice, we just change from pressure to volume. And then the total volume is equal to the summation of all volume. Okay. And then this is called Amagat law. So it is a summation of all volume of all the species will make it a total volume. Okay. And let's go to the next example. Okay, so in this example, we have acetone in a liquid. Liquid acetone is fed at a rate of 400 liters per minute. So this is a volumetric flow rate. Okay, into a heated chamber where it is vaporized into a nitrogen stream. Here we have a nitrogen here. So the gas leaving the heater is diluted by another nitrogen stream. Okay, there are two nitrogen streams at a rate of 419 meter cube per minute. Okay. The combined gas are then compressed to a total pressure of 6.3 atm at a pressure of 6.3 atm and a temperature of 3 to 5 degrees C. And then the partial pressure of acetone in this stream is this one. The atmospheric pressure is this one. Okay, so we have to find what is the molar composition of the stream leaving the compressor, and B, what are the volumetric flow rate. Okay, this is what is the value of molar composition. Okay. It could be Y, okay, and the volumetric flow rate, which is V, entering the evaporator if the temperature and pressure this stream are this one and this one. Okay, so we have a mixture of gas here. Okay, we have a nitrogen and acetone. This acetone will vaporize, become a liquid. So it will vaporize, become a gas. So it will be two gas, which is acetone and nitrogen. Okay, let's go to the solution. Okay, so we have to draw a process flow sheet. There are two equipment here, which is a compressor and a evaporator. Okay. And then we have to label the information we have here. Okay, it's about the feed the first nitrogen stream, okay, at this temperature and pressure. And then we have a liquid of acetone, and we don't know the temperature or the pressure. It doesn't mention in the equation. And we have another nitrogen stream here. Okay, this one, another nitrogen stream at this volumetric flow rate, and we have a compressor, and this compressor will compress until we get 6.3 atm and 3 to 5 degrees C. Okay, let us proceed to how to calculate a molar flow rate of acetone, which is the value of N2. In table B.1, which is an appendix, there is a table that lists out all the property of all the components. Okay. And from that property, we can determine the liquid density of the acetone. I will attach this table together in a Google Classroom. Okay, so this is the table about acetone. So from this table, we have a molecular weight, we have a specific gravity, we have a temperature, critical temperature, critical pressure, and later on you're going to use this one and this one for your energy balance. But in my part, you only need to use critical temperature and critical pressure, which is later on we see how to use it. But here, what I want to tell you that when you have a liquid, or you have a gas, what are the information that you can get, or what are the information that you can extract? One of the important property of a liquid is a density. So you can find a density of any chemical in table B1. Okay. And then we can determine the value of N2, because once we have a volume and then we have a density, we can get a mass, and then from mass we divide it by molecular weight, we can get the mole. Okay, so this volume time this specific gravity, it should be specific gravity of the acetone, and then divided by molecular weight of the acetone, you will get the mole of acetone goes into the system. Okay, and then we move to this stream whereby we can get the value of P, which is P gauge plus P ATM. Okay. Oh yeah, I forgot. This is the value of mole flow rate of the acetone goes into the system. And then next we move to this stream. We can determine the value of P. Okay, and then we can get the value of P, which is, this is a unit conversion from mmHg, from ATM to mmHg. So we add the atmospheric pressure, so we get the value of total pressure, because here it is gauge. Okay, so we have to add the atmospheric pressure, and then from there we can try to find the value of Y4, which is mole fraction of acetone in this stream. Okay, you might be wondering, do we need to do a degree of freedom for this system? For this time being, you don't need to do it yet, because here we try to extract all the information from the equation, and we try to manipulate, not to say manipulate, we try to interpret, we try to use the given data so that we can expand more, so that we can get the unknown value. Okay, that is what we do right now. The first one we solve for this stream. So this is the first. Now I'm going to solve for this stream. Actually, you can choose to solve any of this stream, and it not necessarily follow the sequence. Okay, so from here, because we have the information of a pressure, which is this one, and we also have the information of partial pressure, so we can determine the mole fraction, which is this one. By using this equation, we can determine the mole fraction, which is Y4. Okay, so we can get the value of Y4. Go to this one. Okay, and then for the mole fraction of nitrogen, it is this one, 1 minus Y4, you get this value. So we done in this stream. Okay, we get the value of Y4, we get the value of this, the value of Y4. The N4 not yet. We move to this stream, okay, whereby in this stream we can get the value of N3 by using PV equal to nRT. We have V here, we have V divided by V standard. Okay, So we can get the value of mole because the formula of V equal to V over mole. Okay, and then we come back to our material balance is we do a overall balance for acetone, which is how much goes in equal to how much it goes out. Okay, that's the value. So which is when we have N2 input equal to output, the mole fraction of acetone time N4. So we can get the value of N4. Okay. It's okay, take your time to digest. Okay. So we already done here and also here. The next thing to do is we go back to this stream. Okay. So we still can do a overall balance for we just do a overall mole balance. Okay, for us to determine the value of N1. Okay, so input equal to output. Okay, and then we have N1 plus N2 input plus N3 input equal to N4 input, and we have all the value of N2, we have N3, we have N4, so we can straight away get the value of N1. Okay, so what are the equation actually? We want to find the volume, right? So to use ideal gas equation of state, the first thing, make sure you convert the unit of a temperature. Okay, you convert the unit of pressure. Okay, please ignore this typo. Okay, and then you can get the volumetric flow rate of this one. Okay, so we get how much the nitrogen goes into the system. Okay. So it's talking about a nitrogen, and it want to find, okay, the molar composition, which is a Y we already defined, and then we have to be volumetric flow rate if a nitrogen at this temperature and pressure. How about this value? Are we using it or not? Let's check it again. Okay. Yes, it is the acetone. Okay. So the question is asking us the volumetric flow rate of nitrogen, which is this one. Okay. The question wants us to find the value of this composition and this one. Okay. So I repeat, the first one, you have to find a specific density or a density from table B1 for acetone so that you can calculate the N2. Okay, and then from there you start to solve for this stream, whereby you can find the value of Y4, which is a mole fraction. Okay, you can find the mole fraction. Once you find the mole fraction, you can find the N3. Just use PV and RT. You are given the value of volumetric flow rate. You can divide it by a standard volume, so you can get the mole. Okay, so this one, and then you do a overall balance, and later on you can get all the unknown, and finally you can determine what is the value of V1. Okay, take your time to digest this example. What are the difference between this topic and previously, which is the different we consider a ideal gas condition. We are considering a gas, the property of gas that really affected by temperature and pressure. That's the thing that we consider, and it is additional work. Okay, so previously we just do a mass balance, input equal to output, or a reactive mass balance. But here you still have to do a mass balance, but the component, the phase of the component is a gas, so you need extra work to do, which is you need to use either gas equation of state for some value, for some property. And that's it about ideal gas. Okay, that's the end of part 1. See you in part 2.